Hello everyone, today we are recording the first model of the course Geologic Hydrogen Accelerator. It's about accelerating your knowledge network and investments in the geologic hydrogen market. So the outcome for this course is that you have like a comprehensive overview that helps you as a professional in the oil and gas industry or as an investor in general to solve the lack of reliable information, and that you get also knowledge about the geologic hydrogen market, and that you achieve the confidence and expertise to make informed decisions. And last but not least, that you are also able to find and size business opportunities in this emerging sector. Today I have Jose with me. Please quickly introduce yourself to the audience and how you are related to geologic hydrogen.
My name is Jose Caceres. I'm a geologist, and I've been working in the oil and gas industry for more than 20 years now. 17 of those years, the last 17 years, in the position of well site geologist, where in this position I acquired a senior status, and I worked in many places around the world. And at the same time, I have a master's degree in sustainable energy development, and I always had that inclination towards clean energy and sustainability. And in the last few years, I got interested in energy transition. And I did some research about geothermal energy and geologic hydrogen. And I consider myself an advocate of both sources of energy. And I created a page in LinkedIn with that purpose, with the purpose of promoting and advocating for these renewable energy sources that are underground in the subsurface. And I will explain later why I call geologic hydrogen also renewable. But anyways, could be some considerations for that. But anyways, those are when born, they don't emit, geologic hydrogen when born doesn't emit carbon emissions. So anyways, so I'm vetted into transferring my skills into geologic hydrogen, and I've been investigating and researching and using my geology background for this purpose. And I'm happy to share some of my knowledge in this interesting brief course.
Okay, perfect. So for everyone, we will also link the LinkedIn page below. So make sure that you follow the geothermal hydrogen page. So let's start with the first model. So the first model is an introduction to geologic hydrogen. The outcome for you as a course taker is that you gain like a comprehensive understanding of the fundamentals of geologic hydrogen. So what does it mean? So about the formation, the exploitation, and also the technologies involved. So let's start with the first lesson. The first lesson is the overview of hydrogen energy in geologic hydrogen. So the first question is like, what are the key differences between geologic hydrogen and other forms of hydrogen production that makes it a unique and promising opportunity? So what's your take, Jose?
Geologic hydrogen, also called natural hydrogen or white or gold hydrogen, occurs and exists in its natural form beneath the Earth's surface, in nature. And contrary to conventional wisdom, large stores of natural hydrogen may exist all over the world, just like on oil and gas, but not in the same places. Water and rock reactions deep within the Earth continuously generate hydrogen, which percolates up through the crust. The question is, does this naturally occurring hydrogen also accumulate in underground traps? The answer is yes, and in a similar manner to oil and gas, but the key difference is that its source of origin, and therefore its occurrence, differs to that of oil and gas. Also, because it is so light, bear in mind that hydrogen is the lightest and smallest molecule in the periodic table. It tends to escape rather than to accumulate. So the trapping mechanism for geologic hydrogen requires very good seals. When we talk about seals, we're basically referring to impermeable rocks. Now the question remains, and only now we are learning more about this, on whether it accumulates in a commercially exploitable way or not. If it does, and if it forms sizable reserves, might be there for the taking, and with technologies used already in the oil and gas industry. But also, very important to consider, is the acknowledgement that natural hydrogen not only is cleaner than fossil fuels when burnt, but it is also renewable. It takes millions of years for buried and compressed organic deposits to turn into oil and gas, into fossil fuels, basically. And by contrast, natural hydrogen is always being made afresh when underground water reacts with iron minerals at elevated temperatures and pressures. Currently, all commercial hydrogen has to be manufactured, either in a polluting way by using fossil fuels or in an expensive way by using renewable electricity. So here we are talking about gray hydrogen and green hydrogen. Gray hydrogen is made by reacting methane with steam at high pressures, and this process is called steam methane reforming. And it is a process that emits millions of tons of carbon dioxide to the atmosphere every year. Now, when or if this carbon is captured and when sequestered underground, we're talking about blue hydrogen. So here we have gray hydrogen, when we have all these carbon emissions going to the atmosphere, and if we sequester these carbon emissions and we leave it deep underground, that will be blue hydrogen. But then the most promising form of hydrogen before geologic hydrogen is called green hydrogen, and it is produced by splitting water molecules into oxygen and hydrogen by a process called electrolysis, which in turn is powered by renewable energy, primarily solar or wind. And it is called green because during this process there are no carbon emissions. But green hydrogen is expensive. It costs about $5 per kilogram, and it could be much more. And this is more than twice as much as gray hydrogen. So now, drilling and producing hydrogen out of the ground should be much cheaper, which is why so many proponents are behind the concept of producing geologic hydrogen. And yeah, that's basically what I wanted to say about your first question, Clemens.
Okay, Jose. So my second question would be, how did you first become aware of geologic hydrogen, and what specific aspects of it captured your interest and motivated you to learn more as a professional with background knowledge in oil and gas?
So I became curious about the possibility of the existence of hydrogen naturally produced underground for the first time about 6 years ago. Why and how? Well, at that time I became interested in fuel cells and green hydrogen and the use of electrolysis for splitting water molecules into free hydrogen and oxygen. And I wondered if natural hydrogen deposits existed in nature. And I did a little research in the internet, and to my surprise, I didn't find much information. And from what I found, the conclusion was that there were no significant accumulation of geologic hydrogen. Following that, and I had that idea set in my mind that there were no accumulation of natural or geologic hydrogen. But last year, I changed my mind when I ran across with an article published by Forbes magazine. The article was entitled, "Forget Oil, New Wildcatters are drilling for limitless geologic hydrogen." Upon reading the article, I got very excited about the prospect of drilling for geologic hydrogen. I envisioned myself working in this niche industry and transferring my skills from oil and gas to geologic hydrogen exploration. I got so excited that I made a video about the Forbes article in my newly created, at that time, YouTube channel. I also decided to research about the subject and gain more knowledge. Also, I ended up changing the name of my already existing LinkedIn page, which until that moment was focused to geothermal energy, and expanded also to geologic hydrogen. So my purpose now was to share information about the subject and generate my own content. More than a purpose, it was now a mission that continues now, and that is why we're talking and having this interview with you, Clemens.
Perfect. So we will also link the YouTube channel for everyone. So make sure to subscribe to it. You can also find like another interview with me there. So, and also like with other big companies from the space like Helios Aragon. So like super valuable content there. So I think definitely the most valuable YouTube channel what you can find about the topic. But nevertheless, now to the third and last question for the model. So what are the most common misconceptions or knowledge gaps about geologic hydrogen that you have encountered among industry professionals, and how do you address them, Jose?
Yeah, let's remember, in the middle of the 19th century, the world faced an energy crisis. Whale oil, which was used as an energy source, it was in short supply. In this scenario, Edwin Drake, an investor at that time, proposed drilling for oil, and investors mocked him. Nobody believed that drilling for oil will yield any good results. Despite this, one day in 1859, in Titusville, Pennsylvania, Drake drilled a well and hit oil, and that's how the oil age began. Now the question is, could something similar happen with hydrogen? In a way, it already has. And here comes the story of the remote village of Buruku in the West African nation of Mali, where in 1986 or 1987, locals searching for water drilled a 100-meter down well, and since the hole was dry, they gave up. Though to their surprise, a mysterious emission was coming out from that hole. And then in 2012, when one worker was looking into that hole while smoking a cigarette, the wind that was coming from there exploded in his face. And luckily, he didn't die. And after this incident, a huge fire was ignited and took weeks to cap the well and extinguish the fire. Also, the incident prompted a businessman, a politician from Mali, his name is Alio Diallo, to further investigate the source of the fire, as he initially thought that it was natural gas, which could possess some commercial potential. So he acquired the rights to prospect in the region near the village, and he recruited a company from Canada for the evaluation of this gas. It was then discovered that the gas being emitted by the well was 98% hydrogen. The discovery in Mali represented proof that large stores of natural hydrogen exist, and that they may exist all over the world, just like oil and gas, but not in the same places. Since the discovery in Mali, hydrogen has been found in France, in a coal mine in the Lorraine region, in the USA, in Brazil, in Australia, Colombia, Oman, Spain, last year also in Albania, in a chromite mine, in Poland, Turkey, where the Chimera seep exists, which has been emanating hydrogen and emitting a flame since the antiquity. Also in Namibia, in South Africa, Canada, Bolivia, China, South Korea, Djibouti, and Morocco. And reports of it exist from the Soviet days in Russia and Ukraine. Though it is worth mentioning, most of these natural hydrogen observations are from seepages on surface, and many of these seepages are associated to surface formation known as fairy circles. So now more and more there is mounting scientific evidence that hydrogen created by natural geological processes represent an untapped clean energy source deep underground that could provide vastly more power than we need. So answers to the question of what are the most common misconceptions or knowledge gaps about geologic hydrogen that I have encountered among industry professionals? Well, the answer, or part of the answer, lays in the fact that industry professionals wonder if the oil and gas industry has drilled hundreds of thousands of wells, why geologic hydrogen has almost never been reported. And I said almost because there were some reports, and we will discuss it too. And why it has been overlooked for so long. And there are many reasons for that. One reason is that hydrogen is scarce in sedimentary rocks, and it is in sedimentary rocks where we typically find oil and natural gas, and also because its generation differs substantially from that of oil and natural gas. Note that hydrocarbons are produced from organic-rich rocks, such as organic-rich shales, which is not the case for geologic hydrogen. So let's dig a bit more on this. When compacted and heated, the carbon molecules in those rocks consume any available hydrogen and form longer chain hydrocarbons. Any hydrogen the oil encounters as it migrates to a porous reservoir rock, such as a sandstone, tends to react to form more hydrocarbons. Hydrogen can also react with oxygen in rocks to form water, or combine with carbon dioxide to form abiotic methane. So the common belief was that hydrogen existed mainly in combination with other elements, forming larger molecules, and not on its own. Another misconception even within the scientific community, was that even if hydrogen was generated underground, it could not accumulate. And why? Because hydrogen is the smallest molecule of all, and it can leak through rocks and will be typically considered, and those seals that are typically good for oil and natural gas will not work for naturally produced geologic hydrogen. So it was unlikely to accumulate. The truth is that yes, it can accumulate, though the trapping mechanisms require seals that are impermeable enough to prevent the hydrogen to leak, or otherwise that can provide the conditions for accumulation. And lastly, historically, when well loggers or drillers classify their boreholes emanations, they rarely bothered to measure for hydrogen. The bottom line, they were not really looking for hydrogen, and they were not looking in the right places with the right tools. And we are going to talk more about this later. And we will see that the source of geologic hydrogen is quite different than the source of oil and gas. I complement what I have just said, quoting Geoffrey Ellis, an organic geochemist at the USGS, and one of the most prominent voices in geologic hydrogen. And I will quote his words from an article published a few months back. Ellis says, "It's not that surprising that it's been overlooked because it is a colorless, odorless gas and microbes eat it really efficiently in the subsurface as it is leaking out of the ground. There could be large accumulations in the ground. We just must figure out where to find them, and we can just drill down there and have this great clean energy source." But Ellis also cautious that while there is a vast potential volume of geologic hydrogen globally, much of it may be too hard to get to. Ellis refers that, and again, I quote his words, most of this is going to be way too deep or too far offshore, or accumulation that are much too small that they will never be economical. He estimates globally that there could be at least 10 million megatons of hydrogen in the ground under the surface, vastly more than 100 megatons that the world now uses for industrial processes. Lastly, Ellis mentioned, so if only 2 or 3% of the 10 million megatons out there can be tapped, that will supply all of the world's demand for hundreds of years. And yes, we don't need to tap the whole thing, we just need a little bit of that. Well, the bottom line, I will say, we only need to tap a very small percentage of this geologic hydrogen laying underground. And potentially, geologic hydrogen could play a significant role in the energy transition and in the energy matrix of the future. But the only way to achieve it is that we need to look for it. Just like we have done for the last 160 years or so for oil and natural gas, we must invest in research and utilize and adapt and tune the available prospecting and exploration tools and skill sets from the oil and gas industry and drill for the stuff.
So now you as a course taker have now like a comprehensive understanding of the fundamentals of geologic hydrogen, the formatation, extraction, and also the technologies involved. Also now you will now have like a critical review of how the situation is and where it will go in the future. See you in the next lesson. Hello everyone and welcome to lesson 2. Lesson 2 is about the formatation and extraction of geologic hydrogen. The lesson outcome is that you, course taker, have like an understanding of the processes of geologic hydrogen formatation and also the methods that are used for the extraction. The first question that I have for Jose is, can you walk us through the step-by-step process of geologic hydrogen and how it's formed naturally within the Earth's subsurface?
Yes. Geologic hydrogen generation is produced in nature by geochemical process. The most recognized are serpentinization and radiolysis. So what is serpentinization and how it works? Geologic hydrogen generation results as a byproduct of continuous high temperature reactions between water mixing with iron-rich minerals, which are common in mafic and ultramafic rocks, which are rocks with a high iron and magnesium ratio. An example of an iron-rich rock is, or minerals are olivine and peridotite, which are minerals common in the Earth's mantle. The name serpentinization comes from the fact that in this process, the mineral olivine or peridotite converts into other kind of mineral called serpentinite. In this process, the iron oxidizes, grabbing oxygen atoms from water molecules and releasing hydrogen. So where are these iron-rich pockets located? Typically, they are found near tectonic rifts, or at the edge of the tectonic plates, basically. And the same are located worldwide. Scientists diving in submersibles have seen this process up close at the volcanic mid-Atlantic ridge, where tectonic plates are drifting apart, and mantle rocks rise to create fresh slabs of ocean crust. At a site known as the Lost City, for the towering white smoker chimneys gushing mineral-rich hot water, researchers measured high amounts of hydrogen spewing from the seafloor. In Iceland, which is situated right on the mid-Atlantic ridge, geologic hydrogen flows have been recorded at some of the hot springs and geothermal wells that dot the country. As we know, Iceland is basically volcanic, and it is in between this European plate and North American plate. So this is a perfect location to find this phenomenon. But the hope for commercial natural hydrogen logically lies closer to potential customers, not in the middle of the ocean. So basically, close to end users on the continents. So prospectors are looking in cratons. And what are the cratons? They are the ancient cores of continents, typically very old and stable part of the lithosphere, very old rocks. They are basically the oldest part of the continental plates, and they are composed of ancient crystalline basement rocks. So trapped within the cratons are bands of iron-rich rocks. Now, where these iron-rich rocks are buried deep enough to be hotter than 200 degrees Celsius and exposed to water percolating from the surface, then the ability to produce hydrogen exists. And it is estimated that the serpentinization should produce as much as 80% of Earth's geologic hydrogen. So that's the main geologic process for producing geologic hydrogen, serpentinization. The second geologic hydrogen generation mechanism is radiolysis. And how does radiolysis work? As radioactive elements in the crust, such as uranium and thorium decay, they emit alpha particles, also known as helium nuclei, along with other radiation that can split water molecules underground and consequently capable of generating geologic hydrogen. So basically separating the oxygen from the hydrogen, releasing the hydrogen by the action of these radioactive emissions. So those are basically the main geochemical processes. The main, again, is serpentinization and secondary radiolysis. There is also the belief that there are other ways to generate geologic hydrogen, like deep-seated hydrogen that exists from primordial times. But this theory is controversial, so we will just focus on serpentinization and radiolysis. And yeah, I guess that answers your question.
The thing with Iceland was also really new to me. I think that's not what is like discussed in a lot of studies. So as you can see, you really get here some valuable real-world examples where we find natural or geologic hydrogen. Nevertheless, let's continue with our second question. So the second question, and also like the last question of this lesson, is what are the key geological factors and conditions that are necessary for the formation of significant geologic hydrogen deposits?
First of all, we start with the premise that the origin of geologic hydrogen is different than that of oil and gas. And we mentioned that in the previous model. Basically, it's different than hydrocarbons. When we talk about oil and gas, we're talking about hydrocarbons. So for geologic hydrogen generation to occur, I'm referring to serpentinization in particular, which, as we discussed in the previous question, is the main source of for generating geologic hydrogen. The requirements are iron-rich rocks that react with water at high temperatures. We're talking about more than 200 degrees Celsius. So beyond generation, which is something that we more or less understand, but beyond that, we need to understand that once the hydrogen is formed, it will travel, it will migrate, and similarly to natural gas, it will find its way through permeable formations, as well as fractures and faults. Also, in its migration path, it will go through loss mechanisms that will relinquish its volume and its capacity to remain pure. These loss mechanisms are basically seeps, as hydrogen travels quickly through faults and fractures. It can also diffuse through rocks. Weak seeps on surface can be observed on the ground associated to shallow depressions, sometimes called fairy circles, which we mentioned also earlier. And what are these fairy circles? According to Isabel Moretti, a geologist at the University of Pau, who has studied this phenomena, the bizarre appearance of a fairy circle is likely caused by the way hydrogen migrates upwards and changes the soil microbiome, which then affects the vegetation, and it leaves these so-called fairy circles. Then in shallower layers of soil and rock, microbes consume hydrogen for energy. In this process, they often produce methane. And also abiotic reactions at deeper levels, hydrogen reacts with rocks and gases to form water, and also methane and mineral compounds. So these loss mechanisms, if we have to summarize, are the seeps, basically it escapes all the way to surface. Then in shallower layers, microbes consume this hydrogen, and also this reaction at deeper levels that generate or create larger molecules. So these three loss mechanisms basically reduce the volume of natural hydrogen. But then finally, to have accumulation, or basically for forming hydrogen deposits, we need a trapping mechanism, just like in oil and gas. So for this to occur, we require that the hydrogen gas, as it migrates through permeable rocks, fractures or faults, encounters impermeable rock layers or a cap rock that prevents its upward migration. Then it can potentially get trapped and form a reservoir, or for the case, geologic hydrogen deposits. Also to note, because hydrogen is the smallest molecule of all, and also we discussed it earlier in the first model, it can leak through rocks that will be typically considered seals for oil and natural gas. Not all hydrogen naturally produced underground is likely to accumulate, but for it to accumulate, the trapping mechanism requires seals that are impermeable enough to prevent the hydrogen to leak, or otherwise that can provide the conditions for accumulation. One such rock that can serve as an excellent cap rock are layers of salt, or similar rocks, so-called evaporites. Since salt is virtually impermeable. In the case of the Mali deposits, for example, the cap rock is called dolerite, which is a magmatic rock similar to basalt. And just like that, there are other volcanic rocks that are really good seals. Volcanic seals, for example, which are horizontal magma intrusions between rock layers that can also potentially be very good impermeable seals or cap rocks. So just summarizing, we have the generation. The generation comes from the interaction of water and iron-rich rocks that has specific minerals like olivine or peridotite. that react at high temperatures, let's say 200 degrees Celsius or more. And then we can have this geologic hydrogen generation. And not only that is required, but also we need to consider that this will migrate as it is generated, and it will find its way through cracks and fractures and permeable rocks. And it will only accumulate if it finds cap rock or a rock that it is impermeable enough for not allowing the hydrogen to continue traveling. So in this scenario, in this case, is when you have these accumulations. So those are the conditions, Clemens.